Hello everyone, welcome to this first video in a series of videos about more complex types of analyses. On the menu today we have linear regression analysis, which is a form of regression analysis which we can use for continuous or quantitative outcomes. In this particular video, we're going to talk about the underlying principles or the basic principles of linear regression. And in the following video, we'll be looking at how we can apply linear regression analysis within SPSS, our program of choice in this case. So a little disclaimer before we get started. All of the data that you're going to be seeing here is either fictitious or not very representative of a real situation. So keep that in mind. These are only for educational purposes, really, to show you how linear regression analysis works. So let's get started. And with getting started, we're going to look at systolic blood pressure. It's going to be the variable, our outcome variable of interest. We want to try to explain or predict systolic blood pressure in this video. And I've taken 5 observations, once again, not a very realistic sample, but 5 observations, 5 individuals, and I've measured their blood pressure, our Y or our dependent variable. And we can see here on the right-hand side the different values for blood pressure of those 5 individuals. Now, imagine that you were asked to predict a 6th observation. Let's say that we would get a 6th observation. What would be the value based on the information that we have be? What would be the predicted value? What would be the best guess of this value? Well, first of all, we can of course look at these data points within a graph. In the case of continuous outcomes, one of the better ways of analyzing these data points is via a scattergram, a scatter plot. And we can see here on the y-axis we have blood pressure, and on the x-axis we have the observations. So we have observation 1, 2, 3, 4, and 5 all plotted in this graph. Now, our best guess for a next, say, sixth observation would be the mean, right? We would expect that any new observation would fall somewhere around the mean. That would be its most likely the most likely value that we would see. And so if we just had these, all we had was these data points, then our best guess for any next random person would be, in this case, 122. That would be our best estimate, our y hat, so to speak. That's why the little hat on top of the y says that it's an estimate of blood pressure. So our best estimate for blood pressure based on these data is 122. So the first thing that we would want to do, because obviously when you look at this model, we can see that the predictions obviously do not really align very well with that estimation, right? So we can see that our estimate would be this blue line, the mean, but we can see that the points deviate quite strongly from this line. So the first step that we are going to do in linear regression analysis is to calculate that variance. So how much does the outcome actually vary? How much spread or how much variance is there in the outcome? And we can do that by calculating the absolute differences from each observation to the mean. So that's what I did here. So you can see that I'm calculating the distance from the line that we've drawn, from the mean that we've drawn in this graph. And we subtract the mean from each individual, each yi. So here we can see that observation 1 has an absolute deviance of 8, and that's correct because our mean was 122, and we see that this data point, the first data point, has a value of 130, so it's an absolute difference of 8. And we can do that for each observation. So we see that the second observation has 25, the next one has minus 17, minus 13, minus 3, etc., etc. Now, we want to know something about the total spread, but when we add up all these differences, unfortunately, they will cancel each other out because we have minus, but we also have positive values. And if we add those all up, our total sum would be 0. And of course, that's not correct because there is not 0 variability. There is variability, but because we have negative and positive deviances, we have to do something with that. And so what we can do is we can square those differences so that they become positive. And with squaring the differences, I mean quite literally squaring. And you can actually visualize that as well. See, we have here the square differences from the mean to each individual data point. Some squares are small, some are large, some are very small. And when we look at those square differences in a table, we can see that they don't cancel each other out anymore because they're all positive. And those square differences we can sum. And as you can see, that results in what we call a total sum of squares of 1156. Now, a little side note, you can actually divide this sum of squares by n minus 1, the amount of observations minus 1, and it will result in the sample variance. And you can take it even a step further by taking the square root of that, and you will have the standard deviation of blood pressure. But that's besides the point, because we are at this point, we're going to be working with this sum of squares. It's going to be a term that you're going to hear repeatedly in regression analysis. But you could probably guess that that is not our best estimate, because somebody might as well have a very different blood pressure than 122, even though it might be its most likely value based on those 5 observations that we had. And we can indeed do that. We can estimate blood pressure better, for instance, by relating an independent variable to it. Like, for instance, the BMI, the body mass index. What if we would relate BMI to blood pressure? Maybe we can explain some of that variance that we saw, some of that sum of square, that 1156 that we saw earlier. Maybe we can explain some of that variance by adding BMI to the mix. So what we are going to do is we're going to try to explain parts of the variance that we saw earlier by fitting a straight line through our data. So what we see here now, we see our observations for blood pressure. We had already seen those, but I've also added now the BMI of each of those observations. So each person has a measured blood pressure, but also has a measured BMI. And of course, we can take the mean of both of those observations. So the mean of blood pressure is 122. And in this case, the mean of BMI, our independent variable or our X variable, is 26.4. And of course, we can plot these data in a new graph, and we'll have something that looks something like this. So instead of the observation number on the x-axis, I've now added BMI on the x-axis. And you can already see a pattern, a pretty clear pattern. And in this case, that's because we have only 5 data points, and I've made the data in such a way that it actually looks very linear. But what we're going to try to do is fit a line through these data in that it fits the best. But how do we determine what line fits this data the best? It could be this line, it could be this line, maybe it's this line. That's the question. How do we determine the line that fits through these data points the best? Well, we do that in such a way that those square differences that we saw earlier are minimized. So we want to have a line in which the differences to the points is minimized. The square differences to the line to the points is the smallest. And we call this method the ordinary least squares, or OLS, which is a method of estimating a best fitting linear function or linear straight line through these data. And it will result in a linear model, a basic linear model. And in this case, we could say that that is y hat is equal to a beta 0 and a beta 1 times BMI. And we'll get into what that all means in a second. The first thing that we'll have to do is we have to determine the slope of our line. And the slope of our line is called our beta 1 or our regression coefficient. And beta 1 is estimated by B1, and B1 is calculated with the following formula. This may look a bit daunting, but we'll get into what everything means. Basically, a lot of things are things that we've seen already. We've seen those differences from each observation of y to the mean, and we see that something similar happens to the observations of x, which is BMI in this case. So all of these calculations are things that we've already seen when we were dealing with the differences from the mean. So what we're going to do in this formula is that for each observation of both y and x, we first determine the absolute differences from their respective means. So that's what happens at the top of the formula. So what we do is for each observation of x, we subtract the mean. We do the same thing for each observation of y, and we subtract that mean as well. And then of those absolute differences, we multiply these differences, and we are left with a product. And we repeat that for each observation. So that's what the sigma at the very start says. So for each observation, we repeat these calculations and we sum all of the products together. And finally, at the bottom, we repeat the same process for the x values. We take the absolute differences, square them, and then sum them up. So it will result in a 1 value at the top and 1 value at the bottom. And when we divide those two, we will be left with the B1 coefficient, the regression coefficient, which is going to indicate the slope of our line. So here you can see the absolute differences from x sub I and from the x mean. Here we see the same thing happening for the y variable, so blood pressure. Here we see those differences, those two absolute differences multiplied by one another. And finally, we see the calculations of the bottom of the formula. I've color-coded them so they can be a bit easier to distinguish. And when we calculate all of that, we get the following values: 227 at the top and 63.2 at the bottom, which results in a B1 of 3.592, which is going to be the regression slope, the slope of the regression line. And what this indicates is it gives us the estimated difference in the dependent variable, blood pressure, for each unit increase in the independent variable, BMI. So in our case here, the regression coefficient indicates that for each unit of BMI that somebody increases, once again estimated on these data, of course, our estimated blood pressure increases with 3.592. And there we have the line. Of course, now we have only got the slope, but we also had some other parameter in that regression equation we saw earlier. So let's follow up with that part of the equation, which is what we call the intercept. The intercept is somewhat of an interesting value. It's the beginning of the regression equation, so to speak. It is the estimated value for the y, for the dependent variable, in this case blood pressure, when the value of x, the independent variable, BMI, is 0. It's a starting value that applies to each individual, but it's a little bit tricky because obviously a person with a BMI of 0 does not exist. So it's a bit of a strange value in a lot of cases. But it's a value that is part of the regression equation because it's a starting point for where our equation begins. And we can calculate the intercept by subtracting the value for B1 for the mean of BMI from the mean of blood pressure. I'll show you what that looks like. So we take the mean of blood pressure and we subtract the value that B1 takes for the mean of BMI. So we can calculate the amount of steps in blood pressure that we would increase when the BMI would be at its estimated mean. Now we saw that the mean of BMI was 26.4. So we take 26.4, we multiply it with our value of the regression slope, which was 3.592. And that will result in a value, and we subtract that value from the mean of blood pressure. And that will result in the value for the intercept, the B0. Once again, that's the estimator of beta 0. And in our case, that's 27.171. And when you look at it in a graph, you can see that the data points are far, far away from where the intercept lies, namely here at the bottom, 27.171 in this case. So it's a bit of a tricky value because once again, there are no individuals with a BMI of 0, but it's a necessary value for the regression equation. Now, a little side note, the interpretation of the constant is not always without meaning. An example would be, for instance, in dummy regression, which is something that I'll touch upon in later videos. And additionally, we can also provide meaning to the intercept by centering our dependent variable. I'm not going to get into that in this video, but maybe in another video I will explain what centering means. But just know that it's not always without meaning. So now we have our finished regression equation. We have the regression equation that looks like so. So we were estimating blood pressure, which was equal to beta 0, which in our case is estimated by B0 as 27.171, plus a beta 1, which is estimated by B1 as 3.592 in this case, times BMI. And as you can see, we now have a new line that fits our data points the best by making the square differences the smallest, and we'll get to the square differences in a second. But with this equation, with this linear function, we can now much more accurately estimate somebody's blood pressure. We can much better estimate blood pressure than we did earlier, where we just had the mean of blood pressure as our best guess. Now we just need to figure out somebody's BMI, plug it into the equation, and we can estimate with more accuracy their blood pressure, which I did in this case for somebody with a BMI of 27. We can plug in the numbers, 27.171 plus 3.592 times 27, the BMI, results in an estimated blood pressure of 124.155. But now, of course, the question comes, how good is that prediction? Because, of course, we still saw that there was some deviancy from that new line. The deviances were, of course, a lot smaller than we saw with using the mean as our best estimate. But there was still some variance in the, from that line left, some residual variance. So what we're going to do is we're going to want to quantify how much variance has been explained, what proportion of variance has been explained by the regression line in contrast to when we had a model with no explanatory variables. So the one that we saw all the way at the beginning when we were just using the mean as a best estimate. So what we'll be doing again is we're going to repeat the same process. We're going to determine the square differences again, and we're going to look at how much of those square differences have been explained by adding this new regression line. And we're going to do that a bit differently. We're going to do that by, once again, looking at those differences, but what we're going to do for each observation, so y sub I, we're going to subtract the estimated value of that person, given their BMI, value for BMI, and square those differences and sum them up, which will result once again in one of those sums of squares. And what we'll be doing is we're going to look at the sum of squares that we have left when we were just using the mean in comparison to when we have the new regression line. So here we have the model again, and I have added the values. The first thing that we're going to do is for each of those observations, we're going to estimate their blood pressure based on their BMI. So what you can see here is that we had person 1, which has a BMI of 29. Their observed blood pressure was 130, and based on our model, we estimate that blood pressure to be 131.34. So it's not exactly the same. It's close, but it's not exactly the same. There is some error, some residual. For observation 2, we see that their observed blood pressure was 147, while their BMI was 31. And we estimate based on this linear model that their blood pressure would be 138.52. And we repeat this process for each and every single observation. And of course, the next thing that we do is we're going to look at what are the square differences between each observation that we observe and the one that we estimate using our model. And we can see that over here in the last column. And once again, because these are not absolute but square differences, we can add them up and they result into a sum of squares, a new residual sum of squares. So the residual variance that is left after adding this regression line. So as you can see, this residual sum of squares is already a lot lower than our total sum of squares that we saw earlier. That one was, if you recall, 1156. This one is only 340. So a good chunk of variance has been explained due to the fact that we added BMI to our model. Now, the last thing that we need to do is, of course, what proportion of variances has been explained by adding BMI. And we can, of course, do that. We can easily do that by relating those total sum of squares that we calculated at the beginning with the residual sum of squares. And we can do that by something called the R squared, or the explained variance. It's the fraction of variance explained in our dependent variable, blood pressure, by fitting the linear function, the regression line, to the data points. And it's the proportion of variance explained in blood pressure by the differences, in this case, in BMI. And we can calculate it as follows. We can take the total sum of squares, that was 1156 that we saw earlier, minus the residual sum of squares that we calculated with the new regression line, and then divide that by the total sum of squares. So we are left with a fraction. Here I have the models compared to each other. So on the left-hand side, we have the null model, the model where we were just using the mean as our best estimate. And on the right-hand side, we were using BMI as an explanatory variable for blood pressure. And we can just plug in the numbers. We saw 1156 total variance, total sum of squares, subtract 340.64, which was a residual sum of squares after fitting the regression line, dividing it by the total sum of squares, which results in a fraction of 0.71. So what can we say? That about 71% of the variance in blood pressure is explained by differences in BMI. Now, that is a very, very large proportion of variance. You will not see this very often, especially in the health and life sciences, because blood pressure is, of course, dependent on a lot of different other variables than just BMI. But in this case, once again, it's just to illustrate what is happening when you do linear regression analysis. So that sums it up basically for the way we calculate and the way we use linear regression. But before we end the video, we're going to talk a little bit about the assumptions that you do when you model something with the use of linear regression. Now the first one, this one may sound a bit obvious, but it's very important, is that there has to be a linear relationship between the dependent and the independent variable, right? So we want to draw a straight line through the data points. There at least has to be a way that we can do that. And it's not always the case, because maybe a straight line is not the best method to describe the relationship that we are investigating. So in this case, I once again have a very extreme example where maybe the relationship is quadratic. Could be different. So there has to be a linear relationship, and that's an assumption that you take when you do linear regression analysis. And if that's not the case, then there may have to be a different technique that you need to use, or you have to find some way of adjusting your analysis accordingly so you can deal with this linear relationship. The second assumption is homogeneity of variances, or also called homoscedasticity, which means that the variance around the regression line has to be the same for all values across the x-axis. So in this case, that means that along the entire x-axis, the variance along the regression line has to be roughly the same. And you can see that right here. There are no deviances as we go up on the x-axis. So when that's not the case, when there is a case of heterogeneity, it would look something like this. You would have these cone-shaped figures. So you can see that for low values on the x-axis, the variance is relatively small, whereas when we have higher values for x, the variance seems to increase. So it's not, there is no homogeneity of variances, which is another assumption that you take with linear regression analysis. Number 3, is that our residuals, the error that we still saw from the regression line to each observation, has to be approximately normally distributed. So when you look in a scatter plot, and I've taken those over here, what we saw is we were looking at the differences from the estimated value for a certain observation to each observed observation, and that was a residual. Well, we can actually take all of those residuals for each observation and plot them in, for instance, an histogram or a PP or a QQ plot. And when you do that, that plot needs to be approximately normally distributed. It's another assumption that we're taking when we're doing linear regression. And then finally, and this is often a little bit of an overlooked assumption, but it's nonetheless very important, is independency of the observations. What that means is that the observations have to be independent from one another. And in other words, that means that a value of a certain observation cannot influence the value of another. So they may not be correlated. For instance, if the sampling is not done entirely random. For instance, if you were to include twins, for instance, the values for twins would be very highly correlated because they are siblings. And twins in this case makes it even a stronger case for dependency. That is not always possible to avoid. Sometimes you even intentionally want to have correlated data, but we'll get into why that is in maybe some other video. And in some cases, you can even take into account that dependency, but that is beyond the scope of this current video.